Hello everyone. Welcome to the class of Advanced Calculus and Numerical Methods 18 MAT 2-1. Today, I'll be discussing a topic in Module 5 Numerical Methods. The topic name is Numerical Solution of Algebraic and Transcendental Equations. In that, we will be discussing Newton-Raphson method. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Numerical solution of algebraic and transcendental equations. Let us first know the definition for algebraic and transcendental equations. So any equations which involve algebraic quantities like x, x square, x cube, etc. are called algebraic equations. So equations that involve polynomial terms like x, x square, x cube, etc. are called algebraic equations. Say for example, x cube minus 5x plus 6 is equal to 0, x square minus 2x plus 3 is equal to 0. So now we will discuss transcendental equations. So equations involving non-algebraic quantities like e power x, log x, sin x, tan x, etc. are called transcendental equations. So these are equations which are containing non-algebraic quantities. So when I say non-algebraic quantities, it might be exponential term, logarithmic term, trigonometric expressions. So these equations, if these terms are involved in the equations, then we say such equations are transcendental equations. Say for example, x log x to the base e minus 10 is equal to 0, cos x is equal to 2e power x. So we observed trigonometric term is involved in the second equation. The first one, logarithmic expression is involved. So such equations are called transcendental equations. Now we will know about a fundamental property to do problems. So this fundamental property is going to help us to select the interval while doing the problems. So given f of x is equal to 0, if there exist two values a comma b such that f of a and f of b are of opposite signs. Say f of a is less than 0, f of b must be greater than 0. Otherwise vice versa, that is f of a might be greater than 0 and f of b might be less than 0. Such that the product f of a into f of b will be always negative, less than 0. Then we can conclude that there exists at least one root within the interval a comma b. So to recognize where does the root lie, in which particular interval does the root lie, the fundamental property is going to help us. So it says that given f of x is equal to 0, we have to find those two values a comma b such that f of a and f of b are of opposite signs. Then there exists at least one root within this interval a comma b. Now let us discuss the two methods that are there under numerical solution for algebraic and transcendental equations. The first method that I'm going to discuss is Newton-Raphson iterative method. Newton-Raphson iterative method. So first let us write on the formula for Newton-Raphson iterative method and then we will see how to work out the problems in it. So Newton-Raphson iterative method is given by xn plus 1 is equal to xn plus 1 is equal to xn minus f of xn divided by f dash of xn, provided the denominator term f dash of xn is not equal to 0. Is not equal to 0. So this is our expression. N takes the value. So we substitute n equal to 0, 1, 2, 3, etc. to get successive iterations. to get successive iterations. Right. So xn plus 1 is equal to xn minus f of xn divided by f dash of xn. X will be the initial value if it is given, fine, or else we are going to find out using the fundamental property. We can obtain the interval where does the root lie. So suppose xn is mentioned for us, then fine. If it is not mentioned for us, then we are going to find it out by the fundamental property. So f of xn will be the given function f of x. From that we find out the derivative f dash of x, right? Then we apply the formula xn plus 1 is xn minus f of xn by f dash of xn. So substituting n equal to 0, 1, 2, 3, etc., we can obtain successive iterations. And we continue doing the iterations until we satisfy the desired accuracy. So when we say desired accuracy, it might be total number of decimal places sometimes, or it might be number of iterations mentioned for us. So with all these basic idea, let us do problems on Newton-Raphson iterative method. First problem, find the real root of the equation x e power x is equal to 2 using Newton-Raphson method. Perform 3 iterations. So given function is f of x is equal to 0 form we should put. So x e power x minus 2 is equal to 0 is the given function f of x. So we substitute x is equal to 0, 1, 2, 3, etc. and find an interval such that f of a and f of b are of opposite signs, so that we can conclude at least one real root lies within that interval. Then we need to choose x naught, which is the initial approximation, and then apply Newton-Raphson iterative formula, successively performing 3 iterations. So let us do the solution now. So very firstly, let us denote f of x as x e power x minus 2. We substitute x is equal to 0, 1, 2, 3, etc. And this helps us to obtain the successive values f of 0, f of 1, etc., which should be of opposite signs. So substituting x e power x minus 2, put x is equal to 0, we get minus 2, which is a negative value. Then we substitute x is equal to 1, and this gives us 0.7127183, which is a positive value. So we observe that we have f of 0 equal to negative and f of 1 is positive. So we can conclude that the real root lies in the interval. Root lies in the interval 0, 1. Because at 0, f of 0 was negative. At x is equal to 1, f of 1 is positive. Hence, we can conclude that the root lies within the interval 0, 1. Now, we need to check whether f of 1 is close to 0 or f of 0 is close to 0. F of 1 is 0.7, f of 0 is minus 2. So comparatively, 0.7 is closer to 0. So since f of 1 is close to 0, we can assume the initial approximation as x naught is equal to 1. I repeat, since f of 1 is a value which is close to 0 compared to f of 0, we can conclude that x naught is equal to 1 as the initial approximation. So since f of 1 is close to 0, let the initial approximation be x naught is equal to 1. Let us assume the initial approximation to the root be x naught is equal to 1. Now we will write down Newton-Raphson iterative formula. Newton-Raphson formula, iterative formula is given by xn plus 1 is equal to xn minus f of xn divided by f dash of xn. So now before continuing, let us find out what is f dash. So we have the given function f of x is equal to x e power x minus 2. So let us differentiate with respect to x. First term we have to apply product rule. So x into e power x plus e power x into 1 minus 0. Differentiation of a constant minus 2 is 0. So applying the product rule, we have x e power x plus e power x. Now let us substitute this in the above formula. So therefore xn plus 1 is equal to xn I will retain as it is. F of xn is nothing but xn e power xn minus 2 divided by xn e power xn plus e power xn. So we have Newton-Raphson iterative formula written, and after writing down the formula, we have substituted both f function and f dash function. Just replace x by xn everywhere and write down this xn e power xn minus 2 divided by xn e power xn plus e power xn. So not necessarily required to simplify. I will call this as equation 1 so that we can start doing approximations or the iterations. So first iteration. Now the first iteration can be obtained by substituting n is equal to 0 in equation 1. So let us substitute n is equal to 0 in equation 1. We can obtain x1 is equal to x naught minus x naught e power x naught minus 2 divided by x naught e power x naught plus e power x naught. We know the value of x naught. We have already written the initial approximation x naught is equal to 1. No? So let us substitute that value here. So that gives us x1 value. So x naught is 1 minus 1 into e power 1 minus 2 divided by 1 into e power 1 plus e power 1. You can make use of the calculator and obtain the answer for this. So first iteration x1 is equal to, since they have not mentioned how many decimal places to be considered, we consider our usual consistency, that is 4 decimal places. So x1 is approximately, rounding off to 4 decimals, it is 0.8679. 0.8679. So this is our first iteration. And we have to perform 3 iterations to obtain the required answer. So let us now go ahead with the second iteration. So second iteration, we substitute n equal to 1 put n is equal to 1 in equation 1. Equation 1 is nothing but the formula what we have done, substituting the obtained f of x and f dash of x. So second iteration, I will substitute n is equal to 1 in equation 1. So we get x2 is equal to x1 minus x1 e power x1 minus 2 divided by x1 e power x1 plus e power x1. So wherever n is there, I am substituting n is equal to 1. You can avoid this step. You can actually directly substitute the value of x1 and get the answer 0.8679 minus of 0.8679 e power 0.8679 minus 2 the whole divided by 0.8679 into e power 0.8679 plus e power 0.8679. With the help of a calculator, this gives us 4 decimal places. Rounding off to 4 decimal places, it is 0.8528. 0.8528. So that's the second iteration approximation to the up to the 4 decimal places. Now with this x2, we are successively doing 3 iterations. That is what is our required accuracy. So performing 3 iterations, we need to conclude our answer. So let us write down third iteration now by substituting n is equal to 2 in equation 2. So substituting n is equal to 2, we obtain x3 is equal to x2 minus x2 e power x2 minus 2 divided by x2 e power x2 plus e power x2. As I mentioned, you can avoid this step if you can directly substitute the x2 value and do. That's also well and good. So x3 is equal to 0.8528 minus of 0.8528 into e power 0.8528 minus 2 divided by 0.8528 into e power 0.8528 plus e power 0.8528. So every time I am substituting the value of x2 throughout. So this on simplification gives us the approximation for x3. So x3 up to 4 decimal places, this is approximately equal to 0.8526. We were asked to perform 3 iterations. So after the third iteration, we can now conclude our answer. If not asked with the number of iterations, if you are asked to do with 4 decimals or 3 decimal places, then your decimal places should be equal. In suppose x2 and x3 are equal up to 4 decimal places, then we can conclude. Here we observe 0.8528 is very close to 0.8526. So next iteration might be converging to 4 decimal places. But since here we are asked to perform 3 iterations, we are concluding our answer up to third iteration. So thus, after 3 iterations, a real root of the equation x e power x is equal to 2 is 0.8526. After performing 3 iterations, a real root of the equation of the given equation x e power x is equal to 2 is 0.8526. So this was the first problem for us. Let us discuss the second problem now. Using Newton-Raphson method, find a real root of the equation x log x to the base 10 is equal to 1.2 near 2.5 up to 5 decimal places. So given function is x log x to the base 10 minus 1.2. That is the given f of x for us. We have to perform each iterations up to 5 decimal places. And up to 5 decimal places, our consecutive values of x must be equal to stop doing the iterations. Here the initial approximation x0 is given for us. So x0 is 2.5. So we don't have to find any interval where does the root lie and all. Directly we take x0 is equal to 2.5 and perform the iterations. So let us consider the given function f of x and find out the differentiation f dash of x. So let us denote f of x by x log x to the base 10, x log x to the base 10 minus 1.2, and from this we can find out f dash of x. So f dash of x will be nothing but the derivative d by dx of x log x to the base 10 minus 1.2. But we cannot find out the derivative directly. We have to convert log x to the base 10 to log x to the base e, and then only we can differentiate. So let us first write down log x to the base 10 can be written as log x to the base e divided by log 10 to the base e. Log 10 to the base e. And 1 divided by log 10 to the base e is approximately 0.4343. And I will write down log x to the base e as it is. Log 10 is a constant, so 1 divided by log 10 to the base e. To the base e is same as saying ln in the calculator. So 1 divided by ln 10 when we perform, we get 0.4343 approximately. And this is multiplied by numerator log x to the base e as it is. So let us write down f dash of x. Therefore, f dash of x can be now written as d by dx of x into 0.4343 multiplied by log x to the base e, which I will directly write down as ln, so the differentiation is considerably easy. So minus 1.2. So we have to now apply x into log x product rule. So this gives us 0.4343. I can retain outside, common for both the terms. And this is multiplied by x into differentiation of log x is 1 divided by x plus log x as it is into differentiation of x is 1. And differentiation of a constant minus 1.2 is 0. So this is giving us 0.4343 into 1 plus log x to the base e. Ln x is same as writing log x. And we observe ln x into 0.4343 is same as writing log x to the base 10. So this can be simply written as 0.4343 into 1 is 0.4343 plus log x to the base 10. I wrote back 0.4343 into ln x. I have written back as log x to the base 10. So this is our function f dash of x. Now we have f of x and both f dash of x. So we can apply Newton-Raphson iterative formula. Given the initial approximation x naught is equal to 2.5. So let us write down the initial approximation. Given x naught is equal to 2.5, the initial approximation. The initial approximation. Now with this, we can write down Newton-Raphson formula. So Newton-Raphson iterative formula is given by xn plus 1 is equal to xn minus f of xn divided by f dash of xn. Let us substitute all the known things. So xn plus 1 is equal to xn minus f of xn is nothing but the given question, which is xn log xn to the base 10 minus 1.2 minus 1.2 divided by the differentiation term. Xn log xn to the base 10 minus 1.2 is the given f of x. Now the differentiation f dash is 0.4343 plus log xn to the base 10. 0.4343 plus log xn to the base 10. See, while finding out f dash of x, it is not a compulsion to convert to the base 10. You can as well consider 0.4343 into 1 plus log x to the base e. But I felt it is convenient because already the function f of x is to the base 10. So we can leave f dash also to the base 10 such that it will be convenient for us to type in the calculator. So this is log xn to the base 10. So in the calculator, log itself. Now we can start doing successive iterations. First iteration, we substitute n is equal to 0 in equation 1. Let me call this substitution step as equation 1. So here we are substituting n equal to 0 to get the first iteration. So we have x1 is equal to x naught minus x naught into log x naught to the base 10 minus 1.2 divided by 0.4343 plus log x naught to the base 10. Log x naught to the base 10. X naught initially is given as 2.5. So we can substitute wherever x naught is there as 2.5. So 2.5 into log 2.5 to the base 10 minus 1.2. The whole divided by denominator 0.4343 plus 0.4343 plus log 2.5 to the base 10. So using a calculator, we can obtain the answer for this first case. X1 is approximately 2.74650. Observe the question. We have to obtain all our approximations to 5 decimal places. So 2.74650. I have fixed my calculator to 5 decimals and obtained this answer. So this is the first iteration answer for us. Now let us perform second iteration with the x1 value, whatever we obtained. So second iteration we obtain by substituting n is equal to 1 in equation 1. So we have x2 is equal to x1 minus x1 into log of x1 to the base 10 minus 1.2 divided by 0.4343 plus log xn, x1 to the base 10. Substitute x1 up to 5 decimal places. We have obtained the answer, no? So let us substitute this value of x1 and obtain the answer for second iteration. So 2.74650 minus of 2.74650 into log of 2.74650 to the base 10 minus 1.2. The whole divided by is there only for the second term, 0.4343 plus log of 2.74650 to the base 10. Again, with the help of a calculator, we can conclude x2 answer as up to 5 decimal places, 2.74065. 2.74065. So same manner when we perform the third iteration, substituting n is equal to 2 in equation 1. Substitute n equal to 2 in equation 1. Equation 1 is nothing but the formula with the substitution of f of x and f dash of x. So there we are substituting successively the required answers. Obtained answers in the previous iteration, we are substituting in the next iteration and obtaining the required answers. So x3 is equal to x2 minus x2 into log of x2 to the base 10 minus 1.2 divided by 0.4343 plus log x2 to the base 10. Log x2 to the base 10. So substitute the value of x2 as 2.74065. So substitution step, I will leave it to you. We can obtain x3 as the approximation, third approximation x3 is obtained as 2.74065. Up to 5 decimal places, the value of x3 is also same as x2, 2.74065. So Newton-Raphson iterative method converges to the exact answer very early with less number of iterations. So thus we can conclude the answer. Thus, a real root a real root of the given equation up to 5 decimal places. Up to 5 decimal places is 2.74065. So why did we conclude this as our answer is, we observe that x2 and x3 are same up to 5 decimal places. That is the reason we conclude the answer for the given equation up to 5 decimal places as 2.74065. Hence the solution. So hope these problems on Newton-Raphson iterative method is understandable. Thank you for watching.